Okay, Assalamualaikum and very good morning. Okay, today we will continue with our last lecture on the vibration. Okay, lecture number 9. Okay, so actually, we already have covered all the syllabus basically, from week 1 until week 5. Okay, from the topic of introduction to vibration until the dynamic vibration absorber. Okay, so today lecture is about revision of all these topics and some of introduction to my research opportunity. Okay, and then after that you have your midterm breaks. Okay, and after that maybe you can continue with project implementation and also the assignments that I need to submit by week 8. Okay, Friday. So please always be updated to your to announcement that has been made at the e-learning website. Okay, for today we will review a little bit on what we have learned before. Okay, and some of the main topics of my research. Okay, which is on the topic number 1 on the active vibration control and active force control. Okay, on how you can control the vibration instead of using the passive method such as the dynamic vibration absorber. Okay, this is more advanced method where we can use a control. Okay, a real-time control of vibrations. Okay, that also works in various operating conditions. Okay, and also the second topic is on the piezoelectric material. Okay, it's one of the smart material that can be used as sensor and actuator for any of the vibration system. And the third one on the noise and vibration characterization of the HVAC system. Okay, it's a air conditioner system. Okay, and topic number 4 is on the dam vibration analysis. Okay, on terms of flow in this vibration from the fluid. Okay, when there is a condition of turbulence and how it can affect the vibration of the structure. Topic number 5 is more towards the what you have learned before on the dynamic vibration absorber. Is one of the method of the in terms of structural dynamic modification, which is SDM. Okay, basically we have 4 methods on we can modify on the mass, stiffness and damping, and also we can apply directly the DVA. Okay. The next one is on the control and engineering analysis. Is one of my expertise also, and how we can use the intelligent control methods. Okay, to control the vibration of any system in the world. Okay, so maybe a little bit on the final exam syllabus explanation and also the test one information. Okay, so just refresh. So we for this vibration part we have 3 course outcome. Okay, the first one, after this course you should able to determine the vibration response for a single degree of freedom system, where you as a student should understand the response in terms of displacement, velocity, acceleration and also frequency. Okay, the second one is you must able to calculate the natural frequencies and mode shape for the 2 degree of freedom system. Okay, that what you have learned before. Okay, and how you can in terms of experimental you have done in EML351. Okay, for the experimental model analysis you can determine the natural frequencies and mode shape experimentally, and from the subject you can calculate and also you can draw it manually. Okay, and the third one, you should be able to design a tuned vibration absorber or dynamic vibration absorber for the system. Okay, so this is what you have learned in last topic. Okay, and also the project that have been given, that you have to able to design the DVA. Okay, to attenuate the vibration of the beam structure due to uh, excitation from the motor, unbalanced motor. Okay, so just to refresh also on the course evaluation. Okay, the final exam as of now remains 60%. Okay, the coursework 40%, 20% for my parts, and another 20% is from the Dr. Ui on the noise part. Okay, so there's some modification on the percentage calculation for the my parts. Okay, the test one that will be conduct later online, 6%. The quiz one that you have done, 6%. Okay, this is one part number 1 and 2 is more on the individual parts. Okay, for the group part is assignment 1. Okay, MATLAB and Simulink. 4%, and also the project for the DVA is also 4%. So it's total 12% from the individual part, and another 8% is from the group part. Okay, so this is the overall revisions. Okay, the first topic that we have learned, is on the single degree of freedom free undampened vibration, where there's only mass, stiffness, and also the response, or the degree of freedoms. So you have to have these three elements for the free undampened vibration. Is the damping equal to 0, no damping elements, so that the vibration is remain as is it. It's not reduced in time because there is no damping. So there is no excitation force, there is no transient period here. Whereas the excitation is directly goes to the clean sine wave like this. Now the equation of motion mx double dot plus kx equal to 0, is from the inertia of the mass and also from the stiffness of the spring. And this equal to 0, of course, because there is no excitation force. For this one, this trial function is xt equal to a cosine omega nt minus pi theta. Omega n is referred to the natural frequency. And then how you can determine the natural frequency? Omega n equal to square root k divided by m. So for the free vibration, basically we want to determine the natural frequency of the system. So the second topic is on the force undampened vibration. There's just another additional of the force here, highlight in the red color. So for this case, the c equal to 0. Also there's no damping. And there's no damping. This will be excitation force, the external force, the ft equal to f naught cosine omega t. So the f naught is the amplitude, the initial amplitude of the force. And this is the equation of motion mx double dot plus kx equal to ft, where there is the excitation force here. The trial function must follow the excitation. So when the excitation force is given by cos, it must have the trial function must follow by cos, so that we can cancel out later. If it's given by sine, so it must follow by sines. So this is the amplitude. The amplitude of the vibration that we can calculate. After we derive the equation and we get into of amplitude here. This is the effect of force, where there's a transient period here. The transient motion. And then when it's a combined motion of the transient plus the steady state, it's become a combined motion like this. It's have a second, just a short period of transient before it become a steady state. So this is very important part of any system that has excitation force. So during this period, when there's a excitation that induce at the natural frequency of the system, so the system become resonance. So make sure you design your system that can avoid the natural frequency of the system itself, unless you will become resonance and your system will be disrupt. So from this, that's the thing that actually you can plot about. Where there's if you still remember, there's a three conditions of the excitations. Where you have some kind of this graph. In terms of amplitude, and this is in terms of frequency ratio. So this is the resonant part. Where omega divided by omega n. Here the below part. Basically when there's a three condition of omega near to 0, omega equal to omega n, and another one is omega is infinite, is too high. Okay, so you can refer to these equations, the formula, okay, where the omega is too small, okay, the below part will become 1 and there's a steady static deflection. Okay, this is f naught. Okay, and then when the excitation is increasing, and then it's equal to omega equal to omega n, so this below part becomes 0. So when you divide, it becomes infinite. So this is the area of resonance. Okay, there's no peak, plot peak here, because it's a resonant phenomena. Okay, and then later when you uh, increase the increase the excitations, okay, the frequency, so later the below parts will become large and is almost towards a zero condition. Okay, so that's the plot that you can be done for the force undampened vibrations. Okay, this is sorry. So this one is for the free damper vibration when the damping element is introduced to the system. Okay, you where there is a free damper vibration, no force, but there's a damping here. Okay, so for this, the damping is not equal to 0. Okay, it's the value. Okay, the excitation equal to 0. Okay, there is no external excitation force. The equation of motion will be mx double dot plus cx dot plus kx equal to 0. Okay, so you have the trial function xt equal to ae lambda t. Okay, where you want to determine the lambda so that you can determine in terms of three different damping ratio. Okay, so there's a additional of equation formula that we introduced is a damping ratio. Okay, which is percentage of damping in each of system or each of the natural frequency. Okay, so is equal to c, the damping coefficient itself, divided by 2m mass and omega n. Omega n is the natural frequency. So for this case, you will determine in terms of three condition. Okay, the underdamped, overdamped, and critical damped. Okay, so for this one, okay, you have a system, okay, like this. Okay, so this is in terms of time, okay, and amplitude. Okay, so you have a system which underdamped. Okay, where this one is damping ratio equal to 1. Damping ratio, okay, is below than 1. Okay, underdamped. Okay, so for the overdamped, okay, the second system, the overdamped, okay, you have a system like this. It's the response. Okay, this is on the damping ratio is over than 1. Okay, it's too large. Okay, this is too small, and there will be case of critically damped. We as an engineer, we always want to design a system like a suspension system to have a damping ratio equal to 1. Okay, that's the most uh, efficient design of the damping system. Okay, so for another topics here is the force damper vibration. Okay, so for this one, okay, there's all of the total of 1, 2, 3, 4, 5 elements here. They have basically have all, which is stiffness, damping, excitation force, okay, the mass, and also the response. Okay, so for this case, the damping is not equal to 0. It's a damping element. Excitation force f naught cos sine omega t. The equation of motion is complete one, mx double dot plus cx plus kx equal to ft. The trial function xt equal to a cosines omega t minus by phase, okay, theta. And this is the amplitude that you get, okay, and also the phase angle equation formula that you get. Okay, for this one, basically, okay, this is the previous part of the where you have a force but you have no damping. Okay, so this one is where the plot is the damping ratio equal to 0. Okay, so by slowly you increase the damping ratio so that you can determine the peak at the natural frequency. Okay, this one you can also draw it, or you can estimate the plot by insert this value to these equations, okay, so that you can have this kind of plot. Okay, so maybe we have a damping ratio of, for example, equal to 0.5. Okay, okay, maybe, and we have this is value of 1 here. Okay, and when you design the damping is equal to 1, which is critical damp, so you can determine the plot some kind like this. Okay, where is equal to 1. Okay, so in between, the value in between this value will be in between this plot and this curve. Okay, so that's basically the single degree of freedom, the general one. Okay, so the next system will be our two example of application on the single degree of freedom. Okay, for the first application is on the rotating umbrella mass. Okay, where you have the excitation force in terms of uh, unbalanced mass here. Okay, so for the system, okay, it have a stiffness damping from the system, overall system, the total mass m, the big M here. Okay, the total mass is including the mass of the system and also the small mass of the rotating mass. Okay, the small mass m, okay, here, the eccentricity, the radius from the center to the unbalanced mass. Okay, angular speeds omega, okay, is a rotating speed if you have a machine or motors to your system and the system is rotate, for example, at 200 hertz. Okay, that should be your angular speed. Okay, and also the time is for the theta is equal to omega t. Okay, so for this case the equation motion is most equal to the tempered force vibration. Okay, is a big M here, the mx double dot plus cx dot plus kx equal to small m. Okay, the mass from the rotating umbrella mass, the radius omega 2 power of 2 and sine omega t. Okay, so basically this is the equation of f. Okay, f equal to ma, where we have m, a is the acceleration of the angular speed is equal to e multiplied by omega 2. Okay, so the trial function will be this, the xt equal to a sine omega t minus theta. Okay, and this should be your final equation. Okay, so for this plot is quite different compared to this one. Okay, okay, the general one where we start from the static deflection of value of 1 here. Okay, but this one is start with the value of 0 because there's the excitation omega at the above part. So when the omega is equal to 0, the overall uh, amplitude will become 0. Okay, so of course when this towards the omega equal to omega ends, okay, when the frequency ratio r equal to 1, so it's going to resonance similar to this. Okay, That's why for the rotating angular mass, it must have a damping. Okay, so if there is no damping, it will become worse, as what we have shown you in the case of the helicopter and also the washing machine. Okay, it can disrupt, okay, the structure, and by increasing the damping ratio, it will become more stable, okay, in terms of vibration. And for the final value is toward value of 1 when you increase the frequency, acceleration frequency, so it's almost become 1, okay, the amplitude. So our next system is on the base excitation. Okay, so the source is from the base, it's a moving base, it's not a fixed base, like for example before. Okay, such as this is a fixed base here. Okay, and also so this is a fixed base here, but for this case it's a moving base. Okay, so for this case we have a stiffness, damping as usual, and a mass, and also the response, and we have additional of yt here, or it can be x1 or x2. Okay, so for the base is a have a excitation in terms of displacement and velocity. Okay, it's not in terms of force but in terms of acceleration, sorry, velocity or displacement. So this is the equation of motion. Okay, after derivation you can get this one, mx double dot plus cx dot plus kx equal to cy dot plus ky. So this will be the excitation to the system. So the trial function also we have for each, okay, for the x response and also for the excitation of y. Okay, so for this we can get in terms of transmissibility. Okay, because here when you divide x over y, output divided by input, so you will get this equation for formula. And then when you try to plot from omega equal to 0, omega equal to 1 until omega equal to the large value, you can get a such of this plot, which is similar to the previous one for the force dampened vibrations. Okay, okay, starting from the static deflection here. Okay, is go towards the resonance. Okay, and then it's going down back to 0. Okay, after the vibration is too high, I mean the acceleration frequency is high. Okay, so for this case it's very special. For whatever value of damping ratio you have, when the frequency ratio omega divided by omega n equals to square root of 2, all the points will cross at amplitude of 1 here. Okay, so you still remember there is six rules of this graph, or maybe can be asked later, and you have to know from this part what is the 6 rules of that. Okay, okay, comes to our next system. Okay, the 2 degree of freedom system, where there's an additional of mass and spring system, and also the response. Okay, so for this one you have the, for the first degree of freedom, okay, it's under free undamped vibration. Okay, there's no damping element here. Okay, you have a mass number 1, stiffness number 1, and response number 1. Okay, so also you have the mass number 2, stiffness number 2, and also response number 2. Okay, so this is the, when it's come to the 2 degree of freedom, you must have a 2 equation of motion. When it's come to 3 degree of freedoms, it must have 3. Okay, okay, it's a word, if you get 2 degree of freedom you just get 1 equation of motion, so that should be wrong. Okay, you must have 2. So the trial function xt equal to xe exponential I omega t. Okay, this is the trial function. Okay, so this is the response of the system. Okay, so you should follow this 4 step. Step number 1, okay, you must derive the equation of motion from the free body diagram here. Okay, in terms of metric forms, and later you replace the acceleration and displacement using this trial function. Okay, okay, and after that, after replacing it, you can get in terms of roots equations, and where you if the value of mass, stiffness if given, so that you can find the natural frequency of omega 1 and omega 2 here. Okay, and after you get the natural frequency value for omega 1 and omega 2, you can replace the value back to the equation of motion. Okay, and then you can find the mode shape in terms of x1 and x2. For example, when x1 move 1 cm here, at the first mode, the m2 will move 3 cm in the same directions. And meanwhile, for the second modes, when the m1 move 1 cm here on the right side, but the m2 will move on the opposite sides, like 3 cm. Okay, so you can refer back to the previous slide. Okay, so that you can understand it. So each of the mode shape, or each of the each of natural frequency, you will get different mode shapes. Okay, mode shape number 1 and mode shape number 2. Okay, okay, so for the next system, okay, is 2 degree of freedom, force undampened vibration. Okay, there's an excitation force here. Okay, okay, the difference is the same as a free undampened, but this one you have a excitation force. Okay, F1 sine omega t. Okay, so this will be the equation of motion in terms of metric form. Okay, and later you can replace the trial function of x1 and x2. Okay, and to this acceleration and also the displacement, so that you can get all in terms of x. Okay, and then for the m part, the mass part and the stiffness part, you can move to the right hand side and it become inverse, so that you can determine the value of amplitude x1 and x2 in terms of this equation. Okay, okay, you can refer in detail in the slide of 2 degree of freedom for the force undampened vibration. Okay, on how to get the detailed solution of this. Okay. Okay, so our next slide is on the dynamic vibration absorber. Okay, the previous slides, okay, that I have made also the video for you. Okay, for the system is actually a single degree of freedom system for the disturbed system, and then we add on the another degree of freedom, is become 2 degree of freedom. But for this case, the added degree of freedom is to counter the vibration of this single degree of freedom system. Okay, sorry. Okay, basically this is similar to the equation of motion for the 2 degree of freedom force vibration. Okay, but you just imagine the M2, K2 and X2 become MA, KA and SA. This is the counter of vibration for this part. Okay, so this is the equation of motion. Actually, they are mostly similar to this, if you can refer and compare. And the solution method is also the same. Okay, where you have to replace the x, okay, using the trial function of this, and later you can move this mass and stiffness part to the right hand side. Okay, and finally you can calculate in terms of x and xa. X will be the response of the system, and xa is the counter vibration uh, from the dva, or the response of the dva. Whereas in the system, you always want to design your natural frequency of dva similar to the excitation frequency of the system. Okay, so you imagine the omega is equal to omega a, where omega a equal to ka divided by ma square root of 2 square root. Okay, when you replace here, it will slash out the ma at the below part, then ka will minus by ka, so this response of the primary system will become 0, and all the vibration will transfer to the dva. Okay, so you have this your system like this. Okay, so basically you have the peak here, what I draw before in the dva lecture. Okay, when you apply the dva, this peak, since it becomes 0, so it will become 0 here, but it will induce to natural frequency. Okay, from this graph, okay, you will have the area what we call the absorber zone, where from the omega E1 effective 1 and 2 until omega effective 2. Make sure when there's a difference in terms of excitation frequencies, it not exceed this below range and upper range of omega E1 and omega E2. Okay, if it exceeds this area, it will coincide with omega 1 and omega 2, so it will become resonant again. Okay, so the rule of thumb to design your mass MA for the system, okay, the mass ratio must be in between this ratio of 0.05 until 0.25. Okay, so that's the thing that you must alert for the system. Okay, next is I want to introduce about the research opportunity for you. Okay, when you come to your final year and you want to decide what type of research you want to do, if you're interested in terms of vibration, there's some listed that maybe I can offer to you. Maybe I can show to you also some of the results from the previous study. Okay, that might that might interested for you to decide. Okay, later. Okay, just to show you some of the history of the student, the takers one from my final year project, and also some of the postgraduate. Okay, for the topic number 1, okay, there's a list of students here that already graduated from 2017 until 2019, and also there's a master student that also been graduate that do research into smart material of piezo, and also on the vibration dam analysis. Okay, and there's another 2 guys that currently ongoing for the master. Okay, similar topic for the dam vibration and also the dynamic vibration absorber. Okay, so your senior now have done in 2 topics. Okay, Jah done for the active vibration control for the initial piezo, and another person is Chiu, doing on the intelligent control methods. Okay, and he also will participate in the Innovate Malaysia 2020. So we wish him good lucks and all the best for the competition. Okay. Okay, the first topic is on the active vibration control. Okay, this is a system actually mostly similar to the single degraph system. Okay, you have a passive system here. Okay, the stiffness and damping. You have the mass, excitation force, and also the response. But in terms of this, we add another algorithm or another parameters where is a control system that you can put a sensor such as a displacement sensor or acceleration sensor to record the motion of the vibration of the mass. Okay, the sensor will send the signal to the computer, the controller, and maybe you can use the PID controller on what you have already learned in automatic control subject, and then uh, it can generate a counter force, okay, to the actuator. Okay, the actuator will move as a control signal given, and it can counter vibration in a real time. Okay, for example, if you have a passive system like DVA, you have very limited bandwidth. Okay, but for this one, you can always have a very wide bandwidth. Okay, maybe for this DVA system, you have, for example, the excitation at 200 hertz. Maybe you can play around 180 to 220 hertz only. But this one, you can, when the excitation force frequency is changed to, for example, 10 hertz, 20 hertz, 500 hertz, the system can always react to that. excitation, because it have a sensor, it can monitor in real time, and it also can counter vibration in a real time. So this will be the equation of motion, mx double dot plus cx plus ks equal to F, where F in detail is Ft from the excitation force and plus the control force Fc, okay, which is actually a counter signal, okay, is actually in detail is a minus, it can minus the signal of counter force and it will become zero in theory. So the vibration isolation system is called active if it uses external power such as actuator to perform its function, and the vibration can be eliminated in a real time with a different excitation frequencies. That is a very powerful system when you introduce the active system. Okay, so actuator can be various. Okay, it can be pneumatic. Okay, it can be piezoelectric actuator, hydraulic actuator. Okay, it depends on what application. Okay. Okay, the next one is also in the active vibration control when you can model the system. Okay, this is an example when we do the experiment using the orbital sender. Okay, we operate it in a real application. Okay, with the sandpaper here, we measure the excitation force, excitation frequency, and then we can model it. Okay, so this is the orbital sender. We do the model analysis. We get the three natural frequency so that we can model as a 3 degree of freedom with the M1, M2, and M3. So later we can couple it with a hand arm model here. Okay, hand arm model is we can take it from any of literature that has been done for the biomedical hand arm model. There's a various study that has been done. We can pick any of the model that we interested, and later we can insert the actuator in between that. Okay, so that we can develop a full model of active vibration control. Okay. So for the system, you can see the difference between PD, proportional and derivative controller, and also the AFC, the active force controller, which is a crude approximation tuning method. Okay, that we compare with. Okay, so you can see the blue one, the passive system. Okay, the PD one, when you add the controller, it reduce here. Okay, and later when you introduce the active force control, it will further reduce the vibration to almost zero vibration. Okay, so from this is EXT is referred to when we have another external disturbance we introduce, how the system react. So where you can see the passive, when the another disturbance is suddenly introduced after the tuning method complete, after the tune is complete, you can see the effect here. But in terms of AFC, it still remain as a uh, yellow and orange color in similar line. Okay, that's the very powerful controller that can be used to the system. Okay, so this is the study, okay, from the previous study when we developed in a real active suspended handle for the power tools. Okay, this is the handle for the parallel mounted handle, and this is the initial mounted handle. Okay, so for the parallel one, you can see what I call it parallel because the actuator is mounted in parallel with the stiffness and damping of the system here, like this. Okay, so for this one, this is the actuator. Okay, you have the base excitation, you have the handle. Okay, so the vibration from the base will transfer towards these bolts and go into the spring and goes to this handle. Okay, so you can also measure the force that induced from the actuator. Okay, this is piezoelectric actuator. It's a much smart material. Okay, and then you can reduce the vibration, of course. Okay, and this is the when we think about this is because the piezoelectric, the weakness is must have a preload. Okay, This cannot just you put on of the table, you just operate it. It cannot be done like that because it have a ceramic material there. It may broke the molecule inside the actuator, and then the actuator may not be function well. So we must have a preload like this in terms of spring. Okay, so they will always account the vibration for that. So we try to move from the system to the system. Okay, the initial actuator mounted. So you can see that the handle will become more simplified in overall, but in detail of this design of initial piezo, the internal part is quite complicated also. Okay, but in terms of overall view is become more simplified and more applicable. Okay, because from this, when you want to apply it to a real application of power tool like this die grinder, it's quite difficult because you have to disassemble everything and you have to assemble back exactly what you have here. But from this, you don't need to disassemble of this system because it's already become a one set. You just need to modify the below part to apply at this power tools. Okay, the second topic is on the piezoelectric sensor actuator. Okay, as what I have explained before, piezoelectrics is a smart material. Okay, why you call it smart material? Because it can react in both as a sensor and actuator. Okay, so when it's a mechanical stress, okay, of movement is given to the these materials, it can generate a electricity, and from the signal of electrical, we can tag it as a sensor. And vice versa, when the electrical excitation is given here, okay, electrical signal is given here, it will move mechanically and it can become actuator. So when you put this patch uh, piezoelectric material on this beam, it can react both as a sensor and also the actuator for this structure. Okay, so this is what you can done also in terms of modal analysis. You can determine the natural frequency of the beam, the first bending mode, the second bending mode. Okay, the third mode is on the first torsional mode, and finally the fourth mode. Okay, is a third bending. Okay, and instead of that, you can also done the characterization of the piezoelectric actuator. Okay, in terms of voltage, frequency, and acceleration. When you keep increasing the voltage and keep increasing the frequencies, and you can determine the response in terms of acceleration in terms of this 3D graph. Okay, when you can determine the performance of the piezoelectric material itself. It's quite interesting basically. So this is on the third topic on the noise and vibration characterizations. Okay, so we measured the vibration and noise that induced from this HVAC system, the air conditioning system. Okay, so basically there's a four type of noise that we cannot hear it directly. Okay, but when we measured it in detail using the sound, okay, using the microphone and astrometer, okay, we can get the exact value of these four annoying noise. Okay, so maybe we can hear each of the noise here. Sorry, maybe I can wait. Okay, so that's the noise that induced from the evaporator. Okay, here towards the blower and towards the cabin. This is the hissing noise from this part of TXV here. Okay, and another noise is on the humming noise. Is from the compressor here. And also the clicking noise from the compressor. Uh, so actually the noise is quite difficult to determine. It's a tuk kind of noise. That's the we call it a clicking or engagement when the compressor get engaged and then it's induced some of the clicking noise or engagement noise. Okay, so basically when in a engine car system it cannot be here in physically, if you put a sensor to that it can be measured. Actually it's a combination of all these noise that actually create some of the annoying noise in your cabin car. Okay, that basically you don't know what is the root cause of the noise. You just a combination of noise, then it become another noises. Okay, so this is another study on the vibration, then vibration analysis. Okay, from the flow induced vibration. Okay, this is the example of the dam spillway. Okay, and this is a water that spill. Okay, so basically when you can have a drawing of this dam, you can exactly draw a detailed drawing like this. Okay, and then you can also find not just a simple beam but also in of the complicated design you can find the natural frequency of the structures. Okay, okay, you can see the first mode. Okay, how its movement of the modes. Okay, and also the exact value of the natural frequency of the dam. Okay, why is this important? Because when the dam is operate, when there is a fluid structure interaction flow from the upstream to the downstream of the area, it may induce a vibration that's similar to this mode shape. So when it induces the same value of this natural frequency, so it will induce a resonance. Okay, so this is example of the graph where we have the model analysis shape natural frequency and the operational displacement shape from the flow induced vibration is quite near. And if we don't notice here, maybe in the worst case it can become a resonance. Okay, that's the important also of the study. Okay, so the next topic on the structural dynamic modification is on the previous handle that I show you. Okay, okay, the parallel handle. Okay, we determine that when we do the uh, natural frequency and mode shape analysis, we found that this below beam is quite weak. Okay, so that it induces a two natural frequency at 238 Hz and 491 Hz. Okay, we are targeting that we want to remove these two natural frequency above 500 Hz because most of power tools operate between 0 to 500 Hz. So if this handle have two natural frequency between this range, so the application range is quite limited because we have power tools that can operate in various of frequency between this range. So after some of the study, this is in terms of stiffness modification. Okay, if you still remember, for the SDM, there are four methods: mass modification, stiffness modification, and damping applications. And finally, the dynamic vibration absorber. So this is on the stiffness modification at the lower beam. And when we do back the model analysis, we find that all the natural frequency below 500 has been removed and it moved towards a larger frequency here. So there's a successful experiment that we're targeting to remove all the natural frequency below 500 Hz. Okay, using the SDM method. Okay, the next topic is on the still under the SDM. Okay, is on the dynamic vibration absorber. Okay, the same thing that's on your projects. Okay, where you have given this design dynamic vibration absorber. Is include a cantilever beam, secondary mesh, two secondary mesh, and how you can determine the natural frequency of the beam based on the length calculation. Okay, the length distance between these nests. Okay, so this project has been successfully applied to this HVAC system aircon pipe. Okay, the previous noise that I've shown you, and it can counter one of the noise that induced, which is humming noise. Okay, when we put to the aircon pipe here. Okay, this is the simulated in the 3D software, and this is the real application, and we do the model analysis. Okay, without DVA you can find there's a various natural frequency, three natural frequency in this range of the operating motor from 100 to 500 hertz, 1, 2 and 3 peaks here. When we apply the DVA, it has been removed to below 100 and upper than 500 hertz. So any operation that operate within this area, so the noise and vibration can be reduced. Okay, so this is the result when we operate the system. Okay, for the original aircon pipe. Okay, you can find the amplitudes here is quite high, and we apply the DVA, and the amplitude is significantly reduced from all this point to this point. Okay, even though it's quite disturbed for the reduced vibration signal, but in terms of amplitude, if you put a microphone for example, you can later clearly hear this noise compared to this noise. Okay, because of the different in terms of amplitude. Okay, so the final topics of my research is on the control engine analysis. Okay, where you can manipulate the control system to become more effective. Okay, this is on the example of how we can avoid. We have the targeted output here reference. For example, it also can be applied in robotics application. For example, okay, you have a reference line here that you must follow. Okay, sorry. Okay, so with the clamping anti-wind up, okay, you can see that. Okay, uh, without the anti-wind up, it's come such an overshoot here. Okay, and with the PID control anti-wind up, it can further reduce the overshoot and follow the track line. Okay, okay, another example of such as PID controller coupled with back calculation anti-wind up. Okay, so you have a detailed view here. Okay, without the wind up system, and with the wind up, instead of going to overshoot here, is early can avoid it. Okay, and turn into this different point earlier, instead of going to up to the follower, maybe it can also overshoot there. Okay, it can avoid the what we call also the saturation line here. Okay, okay, this is another study when you can tune the vibration using the intelligent control methods. Okay, such as crude approximations, fuzzy logic, and also the iterative learning method. Okay, this is the similar model that you also have been experienced in your lecture before, previous lecture. Okay, where we can design the control system here, the CA, the fuzzy logic, and IIM method. Okay, so you can see this is the results of the passive system. Okay, actually the blue one, when we zoom in, uh, we cannot see the amplitude anymore because it's too high. And this is the PID. You can see is a vibration reduced from blue to this red line. It's still high. Okay, but when you apply this active force control method using this intelligent method, you can see all of them in this line. Okay, so when you further zoom this area only, okay, this is a red and blue is from the previous passive and PID with a large amplitude, and when you detail it in terms of AFC, you can find out, okay, which intelligent control method can give the best performance. Okay, from this we can get the fuzzy logic, the purple one, the crude estimation, yellow, and the green one is the best for the IIM iterative learning method. Okay, so that we can decide which type of intelligent control that give the best performance for your system. Okay, this is just to show you on the what we have participated before as a team in the vibration lab led by the Prof Zaidi. Okay, for the ITEX 2013, okay, we have won the gold medal here. Okay, for the passive adapter to reduce the vibration of the grass trimmer. And also this is Innovate Malaysia in 2015. We as a team go there and we won all the prizes for the best in category, best paper award and best video award, where we also use for the grass trimmer, but this one is using the active vibration control method. Okay, this is when I go to the conference in Slovenia and meet the in vibration we have a Prof Motorshed here. He is a very famous one in vibration field research study. Okay, it's very pleasure for me can meet him during that time, and he's also the examiner for Prof ID when he doing his PhD back in UK. Okay. Okay, so that's all for today. Maybe I can show you some of hint for the final examination letter. Okay, so for the final examination, there will be 6 questions, 3 from vibration and 3 from noise. Okay, for the vibration part, of course, you have to cover all the topics from lecture 1 to 8, covered for single degree of freedom, 2 degree of freedom, and dynamic vibration absorber. Okay, some complicated equation will be provided, of course, but not including the simple equation like omega equal to pi f, the frequency ratio omega divided by omega n. This will all not be given. Okay. Okay, some of the tests, one announcements. Okay, I'm still planning that we will have a test on 8 April 2020 Wednesday, but it's subject to the USM latest announcement. But based on the VC, whatever it is, the lecture must be continued by online or test by online by 5th of April after the mid-sem break. Okay, the method will be online, but I'm not detailed it yet. Okay, maybe if during that time you still have yourself at home, maybe we can do it in evening. Okay, since I know it is very difficult for you to do in the morning. Okay, this is the targeted time. Okay, even though it's online, you still must prepare your paper, stationery, and calculator at home. Okay, and of course the topics will cover all the topics that we have learned. Okay, if the detailed method is explained, make sure you be there on time so that we can properly do it online. Okay. Okay, the last but not least, thank you and good luck for you to participate in this lecture. Okay, so this is just the picture of our team. Okay, from the vibration lab, including Prof Zaidi, Dr. E, Dr. Fahana, Dr. Abdullah. Okay, when we conduct the annual ICVSSD conference, maybe later on, if you do some research in vibration or you continue master or PhD, maybe you can join us in this conference to present your result of your research so that we can discuss and further find what is gap in vibration to contribute for the society in terms of vibration, and also to contribute to the world with our knowledge. Okay, so that's all for the today class. Thank you very much and enjoy your class.